Thank you, Professor Chen, and thank you for coming. I'm really pleased to be able to share this work of mine. So yes, today I'm going to talk about mathematical practice, and in particular, some ideas from Kant and a reading of Frege's logic. Obviously, you don't know Frege's notation. You're going to see quite a bit of it. I just want you to sort of look at it and watch what happens. I don't expect you to be able to read it. So mathematicians in their practice appear to establish, one way or another, fully contentful, non-trivial truths that extend our knowledge. And at least in some cases, they do so through a course of deductive reasoning from the contents of concepts, from definitions. My aim is to clarify how this works, how it is that by deductive reasoning on the basis of definitions of mathematical concepts, one can discover substantive and novel truths. Two distinctions, that between reports and displays of reasoning, and that between mechanical and mathematical readings of displays of reasoning, prepare the way. How do the signs that mathematicians employ in their work function? Often, it is assumed that such signs are mere abbreviations of words of natural language, and certainly in some cases, they are. But in the most interesting and important cases, signs employed in mathematical practice belong to distinctively mathematical languages within which to display the contents of concepts in mathematically tractable ways, in ways enabling rigorous, rule-governed reasoning in the system of signs. Kant's reflections on the practice of mathematics concern just such cases. Already in his inquiry of 1763, Kant contrasts the method of the mathematician with that of the philosopher. First, whereas in mathematics, figures and signs show in their composition the constituent concepts of which the whole idea indicated by the word consists, the signs employed in philosophical reflection are never anything other than words. One has to focus one's attention on the thing itself, the universal in abstracto. A mathematical language, Kant suggests, not in so many words, is a Leibnizian characteristica. Combined in complexes, its primitive signs serve not merely to abbreviate words, but to display in a written array the contents of mathematical concepts. And because the contents of concepts are displayed in such complexes, reasoning in the system of signs can be made fully rigorous, governed by antecedently stated rules of their manipulation. The language, that is to say, is also a Leibnizian calculus ratiocinator. In philosophy, by contrast, there is and can only be abstract reflection, reflection on what follows from this or that universal idea. In the first critique, the mathematician is described as making an intuitive use of reason through the construction of concepts, a use of reason that is contrasted with the philosopher's discursive use of reason directly from concepts. Kant writes in the first chapter of the Doctrine of Method, philosophical cognition thus considers the particular only in the universal, but mathematical cognition considers the universal in the particular, indeed even in the individual, yet nonetheless a priori and by means of reason. So that just as this individual is determined under certain conditions of construction, the object of the concept to which the individual corresponds as its schema must likewise be thought as universally determined. In mathematics, according to Kant, one considers the concept in concreto, although not empirically, but rather solely as one which it has exhibited a priori, that is, constructed, and in which that which follows from the general conditions of the construction must also hold generally of the object of the constructed concept. According to Kant, then, complex signs in the mathematical practice of concern to him are constructions of concepts that can be manipulated according to rules to yield results that are at once ampliative, extensions of our knowledge, that is, synthetic, and also necessary, a priori. But again, despite the impression Kant gives, even in mathematics, there can be what Kant thinks of as a discursive use of reason directly from concepts. Consider, for example, the ancient Greek proof that there is no largest prime number. One begins by supposing that there are finitely many prime numbers and that one has an ordered list of all of them. Now consider the product of all those primes plus 1. So you've got a list, multiply them all together, add 1. We know from previous work that this number is either prime or has a prime divisor. If it is prime, then obviously it's larger than any prime on our list, contrary to our supposition that we had a list of all the primes. And if it's not prime, then it has a prime divisor that is larger than any on our list, because our number is the product of all those primes plus 1. And that again contradicts our assumption that our list includes all the primes. It's false that there are finitely many primes. There's no largest prime number. This little chain of reasoning obviously requires no signs of mathematics. No such signs were used. Instead, one is told what to do. That is, what and how one is to think, what to suppose and consider, what to infer from what, and so on. And in order to be convinced of the result, one needs actually to do what one is told to do, actually to think about the relevant ideas and draw the relevant inferences. The original set of spoken or written sentences, then, only provides a description or a report of the reasoning. The reasoning is something that must be gone through mentally by directly reflecting on mathematical ideas and what they entail. Mathematicians spend a lot of time scribbling. But, we've just seen, one can also reason mathematically and discover thereby significant mathematical truths just by thinking, by reflecting on mathematical ideas and what follows from them. It can happen as well that reasoning that at one point in history can only be reported later comes to be displayed in a specially devised system of written signs. A very simple example is the reasoning to show that the sum of arbitrarily many even numbers is even. Euclid had no way to display what it is to be an even number. He can only report in proposition 921 the relevant step of reasoning. So we start by assuming we have arbitrarily many even numbers. A, B, B, C, C, D, D, E. They're added together to make AE. What is to be, whoops. Did I do something? That's all right. And here we were saying, oh, the technology nowadays is so smooth. Yeah. But apparently not. Okay. So, very good. We got it. Whatever I did, I'll try not to do again. Okay, so here's the report of the reasoning in Euclid's demonstration. This is what Euclid says, or English translation thereof. Since each of the numbers, a, b, b, c, c, d, d, e, is even, it has a half part by the definition of even, so that the whole also has a half part. But an even number is that which is divisible into two equal parts. Therefore, AE is even. That's what Euclid gives us. We know that each summand has a half part by the definition of even, and on that basis, we are to infer that the sum, the whole, has a half part, and hence is even. But by what right do we draw such an inference? No rule has been given to legitimate the inference from the claim that each summand has a half part to the claim that the sum has a half part. And although the inference seems intuitively to be good, the fact that it seems to be good, even obviously good, is not enough to show that it is good. Just as in the case of the proof that there is no largest prime number, what we have here, in the slightly paraphrased words, each of the summands has a half part, so the sum has a half part, is only a report of reasoning. One is being told to draw an inference. One is not shown the inferential step. It is not by looking at or listening to the words that one knows that the inference is good. One must think about what the words mean and what else must be true given the situation they describe. Euclid can only report the reasoning to show that the sum of arbitrarily many even numbers is even. Once the symbolic language of elementary algebra had been devised, it became possible to formulate, that is, exhibit or display the idea of a sum of arbitrarily many even numbers in the system of signs. We can show now, rather than merely say, what it is to be such a sum. There we are. It is worth spelling out a bit just how this complex of signs works to display the idea of the sum of arbitrarily many even numbers. We're so familiar with this, we forget how much how much thought goes into it. First, we express the idea of an even number as 2a, where a is some positive whole number. And this works because an even number is a number that has a half part that can be divided into two parts without remainder, as, of course, the ancient Greeks knew. We then express the idea of an arbitrarily large sum of such numbers using the plus sign, various letters of the alphabet, the ellipsis, that is the three dots, and the letter n in its distinctive role of indicating not only an arbitrary positive whole number, but also one that is arbitrarily large. That is, the letter n here serves not only as a placeholder for an arbitrary positive whole number, but also to indicate that the number of summands there may be in place of the ellipsis can be arbitrarily large. Now we apply an antecedently specified rule of elementary algebra, namely that AB plus AC equals A times B plus C. And that gives us 2 times A plus B plus C plus ... plus N. This is manifestly an even number. And so we are done. Whereas before, in the case of Euclid's report of the reasoning, we just had to get the goodness of the inference from the claim about all the summands, that each had a half part, to the claim about the sum, that it too had a half part. Now we can display the inference in a bit of paper and pencil reasoning by appeal to an antecedently stated general purpose rule in justifying it. Whereas before, we had a report of an essentially private mental act of reasoning, now we have a display of a public act of reasoning in a specially devised system of written signs. This is a mathematical language. The claim, then, is that although mathematicians do sometimes make what Kant thinks of as a discursive use of reason directly from concepts, they can also devise written systems of signs within which to display the contents of mathematical concepts in ways enabling rigorous, explicitly rule-governed reasoning in the system of signs. What we need now to see is that such systems of written signs can in turn be read in either of two essentially different ways, either mechanically or mathematically. Suppose that you needed, for whatever reason, to construct a particular equilateral triangle, a material instance of that geometrical shape. You thought, I think this wall here really needs an equilateral triangle. I want to make an equilateral triangle on that wall. You might proceed as follows. First, using a straight edge, you draw a line, the length of the side of the desired triangle. Now, using a compass, you draw two circles, one with one end of the drawn line as center, the line as radius, the other with the other end of the drawn line as center and the line as radius. Then from one of the 2 points of intersection of the two circles, you draw, again, using a straight edge, one line to a line to each end of the original line. The three straight lines that you've drawn form a physical instance of a triangle, all three sides of which are close to equal in length. So the triangle you've drawn is an equilateral triangle. It is furthermore clear, given that your aim was to produce an actual instance, remember we're doing this over there on the wall to make a triangle, to produce an actual instance of an equilateral triangle, you were well advised to use a straight edge and compass so that your straight lines would be as straight as possible and your circles as circular as possible. Only by some such mechanical means will the sides of the particular triangle one draws approximate as closely as possible lines that are straight and all equal in length as required by the task that was set. One could, of course, also build a machine to perform such a task. Consider now a mathematical demonstration of the construction of an equilateral triangle on a given straight line, such as that Euclid provides in proposition 1.1 of the elements. The demonstration uses essentially the same collection of marks on a page, with one essential difference. One does not, in the mathematical case, need either a straight edge or a compass. And one does not because one is not aiming to produce a particular triangle. The task is to demonstrate something mathematical, namely that it's possible, given a finite straight line, to construct an equilateral triangle on that line. The demonstration is general throughout. Of course, one does draw a particular sort of straight line, then two particular circles or curves that look sort of circular, and then two more sort of straight lines. But it's not their actual shapes that matter to the mathematical reasoning. What matters is the way the drawn lines are intended to formulate conceptual content usable in the process of mathematical reasoning. In the context of reasoning in Euclid, a circle, for example, serves to license certain inferences. If one has two radii of one and the same circle, then one can infer that they are equal in length, whether or not they look equal in length in the diagram as drawn. They might look really unequal, but as long as the radii of a circle, one circle, the inference goes through. The proof is not mechanical, as it was in our first case involving a straight edge and compass, but is instead mathematical. We establish that the sides of the triangle are one and all exactly equal in length, not by measuring or some mechanical means of production, which obviously could not establish what is wanted, but by reasoning, in particular by inferring that the lines are exactly equal in length because they are all radii of mathematical circles of precisely the same size. In the case of the construction of some one actual equilateral triangle, one draws lines in a stepwise fashion that eventuates in some physical thing that has a certain shape. The construction goes through, the triangle is produced. Whether or not that which is producing it, whether human or machine, has any understanding of what it is doing. In the mathematical proof, although the array of lines may be drawn in a way that is visually indistinguishable from the array drawn in the case of the production of some actual triangle, there is no proof without the reasoning one does in the diagram. The mathematical proof lies first in judging that all three lines are and must be equal in length, because they are all radii of two circles of precisely the same size. And having realized in this way that the three lines are equal in length, one must then see that the three lines, differently regarded, form a triangle. That what had been seen as radii of circles can also be seen as sides of a triangle. To see that they're equal in length, you have to see them as radii of circles. To see that you've drawn a triangle, you have to see them as sides of a triangle. This perceptual skill of seeing something now one way and now another is essential to one's getting the proof as a proof of a mathematical result. In the mechanical construction, the drawn lines are just that, drawn lines. In the mathematical proof, the lines serve a much more interesting and conceptually subtle function. I think this really is subtle. In the context of Euclidean diagrammatic reasoning, a drawn straight line expresses a Phrygian sense independent of any context of use. Only given its place in a certain diagram and a particular way of regarding it does it designate, say, a radius of a circle or a side of a triangle. So I'm saying Frege gives us the tools to understand what's happening in Euclidean diagrammatic reasoning. Point is subtle. I'm going to give you a different example. Again, a very simple example to illustrate the essential point. Imagine a person who knows how to count things, but not any arithmetical facts, even the most basic, so not even 2 + 3 is 5. Imagine further that this person wishes to know what, say, the sum of 7 and 5 is. A good mechanical expedient for finding the answer would be first count out 7 things, then count out 5 more things, and finally count the resultant collection, something we can do with marks on a page. The collection on the left is a collection of 7 strokes. That on the right is a collection of 5 strokes. By adding 5 more strokes after making the first 7 strokes, I made, whether I knew it or not, a collection of 12 things, right? If you have 7 things and you add 5 more, you've got 12. I can learn that by counting the whole. That there are 12 strokes is already there, contained implicitly in the display, as soon as 5 more strokes are added to the original 7 strokes. What my subsequent counting does is only to make that fact explicit. You got 7 strokes, you add 5, you got 12. Kant does not think of the problem of the sum of 7 and 5 in this way. He discusses this case in the B introduction of the critique, the first critique. According to Kant, the truth that 7 + 5 is 12 is not analytic. 12 is not already there, but instead synthetic a priori. But if so, then being 12 is not contained already in the given numbers 7 and 5. Rather, Kant thinks, the number 12 can be constructed given the starting point, not in a mechanical way, but mathematically, in a way that reveals a mathematical truth. And we can see how this is to work if we conceive those strokes not as mere things, marks that perhaps also stand for other things, but instead as primitive signs of an exceedingly simple mathematical language, the most simple mathematical language you can imagine. Again, as signs that express Phrygian senses. So the stroke by itself just expresses a sense. We then use those primitive signs to construct complex signs that designate numbers. On this mathematical reading, the collection of 7 strokes is not merely a collection of marks on a page. It is instead a complex sign of a specially devised written system, a sign that, although complex, nonetheless designates one thing in particular, namely the number 7, a certain mathematical object. And it does so through a Phrygian sense that reveals that number as a certain multiplicity. So this complex sign designates the number 7. On this reading, the individual strokes in the complex sign do not designate. Only the whole complex sign, the whole collection of strokes read together as one sign, designates. And once we have 2 such signs, complex sign for 7, complex sign for 5, we can construct mathematically, not mechanically, a sign for the number 12 by combining all the primitive signs into one. This is a mathematical operation, not merely a mechanical one, insofar as, first, we're using the strokes to display the arithmetical contents of the numbers 7 and 5, what it is to be those numbers, namely certain multiplicities. And subsequently, on the basis of that displayed content, we manipulate the primitive signs in a rigorous, rule-governed way in order to show something about the numbers involved, that the sum of the numbers 7 and 5 is the number 12, a properly mathematical result. So here's the key idea. In a bit of mechanical reasoning, the signs, the written marks, are nothing more than counters to be manipulated in certain ways according to rules. They designate what they designate independent of any context of use or way of regarding them, and there's no need at all to take into account what it is that they designate in making the constructions. A straight line is a straight line, whether or not anyone notices. A circle is a circle, whether or not it is taken for one by anyone. And so for the collection of strokes. There are as many as there are in a collection of them, independent of anyone's knowledge. The fact that they stand in for other things is irrelevant. That's all in the mechanical side. In the case of mathematical reasoning, the signs function very differently. They are not, in that case, merely counters to be manipulated according to rules. Instead, the signs express Phrygian senses. And independent of any context of use, that's all that they do. Such signs, or complexes of them, designate this or that mathematical concept only within a context of use and relative to a way of regarding them. So we've just seen that at least some collections of written marks can be read either mechanically or mathematically. In fact, the point holds for any Leibnizian language. Because it is a calculus ratiocinator as well as a characteristica, a Leibnizian language within which to reason on the basis of the contents of concepts can invariably be read also mechanically. Its employment as nothing more than the mechanical manipulation of signs according to rules, something a machine could do as well as any rational animal. This is precisely what happened in the case of Frege's concept script. Although Frege designed his Begriffsschrift as a Leibnizian mathematical language, as at once a characteristica within which to display the contents of mathematical concepts, and as a calculus ratiocinator within which to reason rigorously on the basis of such displays. The language was read mechanically. And because it was so read, it was taken to be a mere notational variant of standard notations of our quantificational logic. So Begerschrift is a mathematical language, not a logic of ordinary language. Already by the time Frege was writing in the late 19th century, Riemann, Dedekind, and others had made it clear that mathematics, as they had come to practice it, involves not an intuitive use of reason, the construction of concepts in pure intuition, but instead something apparently like Kant's discursive use of reason directly from concepts. Eschewing the practice of constructive algebraic problem solving that had dominated mathematics throughout the 18th century, these mathematicians instead began proving theorems deductively on the basis of their analyses of mathematical concepts. Kant, it thus came to seem, was wrong about mathematical practice. Many philosophers assumed that Kant was nonetheless right about logic, that logic is a purely formal discipline without content of its own, and that by logic alone, only analytical results are derivable. Frege disagreed. Indeed, it may be that Frege thought Kant was wrong about logic because Kant was, as it turned out, wrong about mathematics. If mathematics is the substantive scientific discipline it seems on the face of it to be, and if mathematics proceeds by reasoning deductively directly on the basis of concepts, then Kant must be wrong to think that one cannot extend one's knowledge by purely deductive means. Frege's proof of Theorem 133 in Part 3 of Begriffsschrift, that's the 1879 logic, is to illustrate exactly that. How one can extend one's knowledge by deductive reasoning from defined concepts. So now we're going to look at this proof, first its definitions, then the nature of the reasoning. So this is going to get a little bit hairy. Okay, we've seen that mathematical demonstrations that at first can only be reported in words can, in some cases, be later displayed in specially divided systems of written signs. We did that for the sum of even numbers is even. Frege's concept script is another example. It was devised to display chains of deductive reasoning from concepts that could otherwise only be reported. We get reports in 19th century mathematics. We get reports nowadays because nobody uses Frege. The first task was to display in definitions the inferentially articulated contents of mathematical concepts, their contents as they matter to deductive reasoning. In Begriffsschrift Part 3, we're provided 4 such definitions, all of which can be read either mathematically or mechanically. The least interesting of the 4 definitions is that of belonging to a sequence, which is merely truth functional, in essence no different from the definition of, say, being less than or equal to. So there's the definition. And you can, okay, so here's the definition. This is the conditional stroke. This is the negation stroke. So this functions as disjunction. It's like, less than or equal to, follows. So we've got a simple sign to abbreviate a disjunction. Z belongs to the F sequence beginning with X is merely to say that either Z follows, that's the squiggly line, or Z is identical with X. Such a definition, because it is merely disjunctive, does not introduce anything new. In Frege's imagery, it does not draw new boundary lines, but only uses old boundary lines in a new way. Such a definition is convenient, but it's not fruitful, just like less than or equal to. It does not enable one to discover anything one could not have discovered without it. It's like less than or equal to. The definitions of being hereditary and being a many-one procedure, because they involve generality as marked by the presence of the concavity in the definitions, do draw new lines. And they do so because they take the form of inference licenses. So, to say of some property F that it's hereditary in the F sequence, so again, there's our defined sign, and there's the definition. From the proposition that D has the property F, that's this condition, whatever D may be, it can always be inferred that each result of an application, so here A is an application of F to D, that A has F. It can always be inferred. That's an inference license. You can't articulate inference licenses in quantificational logic. To ascribe the higher level property being hereditary to some lower level concept F relative to a procedure F is thus to issue an inference license in regard to that property. If you have an object that is F, then you can infer of anything that is the result of an application of the procedure to that object that it too is F. So for example, being human is hereditary in the offspring sequence. If something is a human, then anything that is the offspring of a human is also human. That's what being hereditary means. Same is true of the definition of being a many-one sequence. There's the definition. And to say that a procedure is many-one, so Frege allows that functions can branch. It can be inferred from the circumstance that E is the result. So E is the result of an application of F to D, whatever D is. Then, for any other result, so A, any A that is the result of the application of F, is going to be identical to E. So, no branching. So, in this way, the concavity, that little cup with a letter in it, together with the conditional stroke, enables the expression of laws about what entails and is entailed by what. So you use the concavity and the conditional stroke to express laws. So we show the content of the concept, what law it contains. But a mechanical reading of these definitions is also possible, one according to which the notation serves merely to record some state of affairs. What is the case if a property is hereditary or some procedure many-one? That's the reading of the quantificational logician. Because the language of quantificational logic was devised to record or picture states of affairs, what is the case if a sentence is true, devised, as Quine says, with no other thought than to facilitate the tracing of truth conditions, this logic serves as a mere, or the definition serves as a mere convenience. The primitive signs as nothing more than abbreviations for words of natural language. That's what we're taught in basic logic, that the signs are abbreviations. We all know how this goes. A definition in standard logical notation or in Frege's concept script, read mechanically, sets out necessary and sufficient conditions. What is the case if the defined term applies and introduces an abbreviation for those conditions? That's the standard reading. Okay, Frege's most interesting definition, following. Of all his definitions, it's this one that Frege singles out as fruitful, as enabling a real extension of our knowledge. Intuitively, the idea, do you want to see what it looks like? Intuitively, the idea that y follows x, so y follows x in the F sequence, means that beginning with x, through repeated applications of the procedure F, one will eventually arrive at the value y. For example, by repeatedly adding 3, beginning with the number 4, you will eventually get to the number 31. 31 follows 4 in the plus 3 sequence. So following just means somewhere down the line, applying that f, you're going to get to y from x. But of course, there is nothing about repeated applications of a procedure in Frege's definition. That's not a mathematical notion. Instead, Frege provides an analysis of that concept, a conception of its content that is mathematically tractable in reasoning. So on Frege's analysis, what it says, from the true propositions that every result of the application of the procedure f to x has f. So if every result, that's the a there, of the application of f to x has the property, and the property is hereditary, that's what this says, then it can be inferred that y has the property f. Frege had not, at the time of writing Begriffsschrift, explicitly formulated the Sinn-Bedeuten distinction, but it's clearly already at work in the language. In particular, in Frege's definitions, both the complex sign, that is the definiens, and the newly introduced simple sign, that is the definiendum, they both designate one concept. They have the same Bedeuten. But the definiendum does not merely abbreviate the complex sign, that is the definiens. So this is not an abbreviation of that. The two signs, simple and complex, express different senses. Indeed, it's manifest that they express different senses because the rules that govern the manipulation of signs in the language can be applied only to the complex sign. We've got rules telling you what you can do when you've got a conditional stroke and a concavity and so on. There are no rules governing that simple sign. It's the definiendum, simple sign, that makes explicit that we are dealing with some one concept. But it's the definiens, the analysis, that serves to exhibit the content of that concept as it matters to inference. So this is like the 7 strokes showing us what the content of the number 7 is. Okay, now we need to understand how definitions in Begriffsschrift matter to inference. In our familiar systems of logic, primitive signs have a fixed meaning. Frege's Sinn-Bedeuten distinction plays no role in such a language. And because Frege's distinction has no role to play, a complex sign in the language, such as one finds in a definition, cannot function at once to display the content of a concept and to designate that concept. Again, a definition in standard logic sets out necessary and sufficient conditions, what is the case if the defined term correctly applies, and it provides an abbreviation for those conditions. It follows that inference in such a language cannot reveal anything not contained already in the premises taken together with which the reasoning begins. Because language, as it is understood in standard logic, is a means of picturing facts, logical inference must be understood on the model of containment. If the information in the conclusion is contained already in the premises taken as a whole, then the inference is valid. Good old Venn diagrams are a good illustration of this conception of inference. First, we picture the information in the premises. All A is B. Shade the area inside the A circle, outside the B circle. All B is C. Shade the area inside the B circle and outside the C circle. But by shading those two areas, we've already shown that all A is C because the area inside the A circle and outside the C circle is all shaded in. Actually, to draw the inference, infer that all A is C, just makes that explicit. You're not learning anything new. Everything was already there in the premises. Notice the very strong parallel between what is going on in a Venn diagram and the case of determining mechanically what is the sum of 7 and 5 using written marks, as we did before. In both cases, one displays or pictures something, namely a fact or collection of things, and one does so by generating a fact or collection. The collection of strokes is to be seen as just that, a collection of things on the mechanical reading. And, as is made explicit in Wittgenstein's Tractatus, a proposition picturing a fact or state of affairs, as on the reading of standard logic, does so by being a fact or state of affairs. Because propositions serve on this account to picture facts by being facts, just as a collection of strokes pictures a collection of things by being a collection of things, valid inference must be understood to be nothing more than a matter of making explicit information that was implicit already in the starting points. It is, as Wittgenstein says in the Tractatus, proof in logic is merely a mechanical expedient to facilitate the recognition of tautologies in complicated cases. There is and can be no ampliative deductive proof in standard logic, as Kant already knew. So on the containment model, an inference is valid just in case the information in the conclusion is contained already in the premises taken together. And in any logic, the sentences of which are understood to trace truth conditions, this containment model is the only model available for thinking about the validity of inference. The situation is very different in a logic that enables the display of the contents of concepts and the expression of inference licenses. In that case, inference can extend one's knowledge. The basic case is very simple. If I know that being A entails being B, being a cat entails being a mammal, then there is a valid inference that can be made from something's being A to its being B. So if I know of some object that it is A, then I can infer that it is B. In such a case, everything that's needed for the inference to the conclusion that the object is B is given in the starting points, in the fact that O is A and the rule that being A entails being B. But that the object is B is not contained already in those starting points. One must actually make the inference, draw the conclusion by applying the rule in the given case. And because the conclusion is not contained already in the starting points, though they provide everything you need, the conclusion extends our knowledge. Frege claims in Grundlagen section 88 that a deductive proof from fruitful concepts can be ampliative. And we know that fruitful concepts draw new lines, and that Frege's definition of following in particular is fruitful. So what we have to see is how that definition of following enables the derivation of an ampliative conclusion. So I'm going to give you an example first of a different example that gives the basic idea. So Euler's theorem, e to the ix equals cos x plus I sine x. Here's Euler's proof. So Euler determined, so think of this as an analysis, the exponential function in terms of a power series expansion, the sine function in terms of a power series expansion, the cosine function in terms of a power series expansion. Again, details don't matter. Replacing x with ix in the power series, all we did was just everywhere there's an x, put an ix. We can do that. And then we do some simple arithmetic, get rid of all those powers, and that gives us this identity. And then we separate out all the terms that do not contain I and all the terms that do contain I, and then pull I out. But what we get there is just the sine and cosine power series expansions. So putting equals for equals gives us Euler's theorem. So what we did was we started with identities, we made some manipulations, and then we put equals for equals. This is a paradigm of a mathematical result that extends our knowledge. The basic form of the reasoning is going to be similar in Frege. So Frege's proofs of his theorems in part 3 of Begriffsschrift are nowhere near as interesting as Euler's proof of his theorem. Nevertheless, they take the same form. The principal difference being that whereas Euler combines content by putting equals for equals after some preliminary preparation, Frege combines content by drawing inferences by hypothetical syllogism, again, after preliminary preparation. So do some preparation and then combine content by hypothetical syllogism. So, for example, Frege shows that properties that are hereditary in a sequence are also hereditary under weakening. So that's the first thing I want to prove. Okay, so start with the definition of following in a sequence. So this is just the definition. We've seen that. And we're going to transform it into a conditional. So the first thing we do is just play around with the expressions. So we're going to pull down the defined sign, make it conditional, and get rid of the concavity. Obviously, we can do that. It's just a simple transformation of the definition. Now we need to reorder conditions. We can think of this. So this is the consequent. We can think of this as the consequent on 3 conditions. The order of conditions, of course, doesn't matter. So we can reorder them. Frege has lots of theorems for reordering, so we just change the order of them. Now we need to reorganize according to the rule in axiom 2. Axiom 2 says, if you have, here's a conditional. So we can think of this as the consequent and this as the antecedent. So this is true on this condition. A conditional on a condition. Then you can rewrite, move that condition onto both arms of the conditional. That's what axiom 2 says we can do. So again, we're just making some changes to the formula. It's just straight logic. Okay, Frege uses theorem 5. We're going to use hypothetical syllogism. Frege, every step is made fully explicit, so it's hard. But I'm just focusing on the important stuff. So this theorem, imagine this sign up here. That's just from the definition of being hereditary. We pull down the defined sign, and then we switch these 2 conditions. We need it in a slightly altered form. We need a concavity there. But now, look, A on condition that B, B on the condition that C. By hypothetical syllogism, A on condition that C. So now we combined content from 2 definitions. But look what we've got. So this is what we just proved. If we reorder the 2 bottom conditions, we get this. If something is hereditary in the F sequence, so if this property is hereditary in this sequence, then it's hereditary even where Y only follows X. So this is a much stronger claim, right? This is Y is the result of an application. It's the very next one. This one says, nah, it can be anyone down the line. It's still hereditary. So this is an interesting claim. If it's hereditary under weakening. Okay, so that what is hereditary in a sequence is hereditary under weakening when Y only follows X is a non-trivial result provable on the basis of the 2 definitions that we started with. And you can see we've got those 2 defined signs in there. Notice further that although the definition of being hereditary contains an inference rule regarding objects and their properties, this rule is about properties. If a property is hereditary, then it can be inferred that that property is hereditary under weakening. So now we've got this rule of inference about properties. This rule would seem to be synthetic a priori. It's like Euler's theorem. We started with some identities, and then we combined content. So, this is a conclusion that I'm claiming is synthetic a priori. It combines content from two definitions in a way that extends our knowledge. Now we need to see that not only the conclusion of a chain of deductive reasoning in Begriffsschrift, but even the reasoning itself can be synthetic a priori. Such reasoning, we will see, is deductive. That is, it's necessarily truth-preserving, but it's not logically deductive. It's not just by logic alone. And it's not logically deductive because it uses a rule of inference that is not strictly logical. Hypothetical syllogism is a strictly logical rule. The rules we need are derived from definitions. For example, it uses this rule, the rule that being hereditary entails being hereditary under weakening. So this rule we derive from definitions, and we're going to use it. Okay, so theorem 133. This is what we're trying to prove. There's the theorem. What it says, so notice all defined signs. We're going to start with definitions, and we're going to prove this. If m and y are the result of an application of x of f to x, then m and y are connected. Remember, this is or, conditional stroke of negation. M follows y in the f sequence, somewhere down the line, or y follows m, somewhere down the line, or m and y are identical, provided our function is many one. This is obviously true, right? If you've got two things, two values that follow somewhere, so you start with x, you've got two values somewhere down the line, no branching, then either the first one comes after the second one comes after the first, or they're identical, right? It's simple. It's true. We like true things. Okay, so we're going to prove this. Frege's plan. That's what we're trying to prove. This is trivial, right? This just comes from the definition of being a many-one sequence. If m and y are the result of an application of f to x, then they have to be identical. We can get the one from the other provided we do two things. This strong claim, y and m are the result of an application of f to x, has to be replaced with they just follow. So that's much weaker, right? They just have to come somewhere down the line. But to prove that, we've got to weaken this, obviously. They aren't going to be identical. They might be identical, but maybe one only follows the other. So that's our strategy, is we're going to try and weaken these conditions. And of course, we're going to use being hereditary to do that. Okay, there's our sort of template that we're going to use. Here, we've proven that belonging to a sequence is hereditary. If y belongs to the f sequence beginning with z, v is the result of an application of f to y, then v belongs to the f sequence. That's easy to prove. Here, we've just weakened this condition to this one. So instead of a and x being identical, then either they're identical or a follows. Here, you can't even see it, but we've just slightly modified this and shown that if a is the result of an application of y, then it always belongs. Then we can show that if m follows, then m belongs. Now we can combine by hypothetical syllogism, because notice this condition is the same as this one. We just need to put a concavity in it. So by hypothetical syllogism, we get this. But notice we've gone from here. Oh, we've changed m. A has become m in the magical process. But notice this is what's important. Instead of a is the result of an application of f to y, we've got that it follows. So we've weakened one condition. This condition is still strong, but this one has been weakened. So we've made one of the moves that we needed to make, weakened a condition. Here we've just replaced, we've made our consequent even weaker. Instead of M belongs to the F sequence beginning with F, we say they're connected. Okay, this is what we've proven so far. We're very close. What we need is this. The only difference is here we've got X is the result of an application of F to Y. Here we've got X follows. So we've got to weaken. We've got to weaken that condition to this one. We know what the strategy is. We have to find a property that's hereditary and use that to weaken the condition. So that's what we have to do. We've already shown that following is hereditary, belonging is hereditary. What's left? It's the property Frege never mentions. It's being connected. He's going to prove that connectedness is hereditary. Remember, this is what connectedness is. M follows X, X follows M, or M and X are identical. That's what connectedness is. So we have to prove that connectedness is hereditary. And that means basically what we're going to have to do is replace this with being connected. If M is connected to Y and X follows Y, then X is connected to M. So that's what we have to show. Frege is going to construct the concept inferentially. There's what we have. This is straightforward to prove. Look at this is just being hereditary. Belonging is hereditary with an extra condition. Frege says it's going to give us that. He proves a rule in part 2. This is the most complicated rule in part 2. He proves it because of this step. So if A on condition that C and D, and A on condition that B, then A on condition that B or C and D. There's A, there's C, there's D, and there's B. A, B, C, and D. So Frege proves a rule that allows him to construct connectedness. This shows that connectedness is hereditary on the condition that the sequence is many one. And now we can finish the proof. There's our rule. If a disjunctive property is hereditary, then it, or something very like it, is hereditary under weakening. It's another weakening rule, and that gives us our conclusion. That is the proof of Theorem 133. What the proof shows is that Frege's analysis of the notion of following in a sequence, so the analysis is given in the definition, enables the derivation of rules licensing inferences that are needed in the proof of Theorem 133. In the case of Frege's proof of Theorem 133, not only is the conclusion ampliative, that is, synthetic a priori in something like Kant's sense, even the reasoning is ampliative. The reasoning is deductive, that is, truth-preserving, but it's not logically deductive insofar as the reasoning depends essentially on a rule derived from Frege's definition of following in a sequence. Specifically, it relies on Frege's analysis. Assuming that Frege's analysis is correct, the rule derived from the definition is truth-preserving, and the inference it licenses is necessary. But it's not logically necessary, not in the way an inference governed by a law of logic is logically necessary. Such an inference is, in its way, yet another instance of the Kantian synthetic a priori. Conclusion. As presented in the 1879 logic, the proof of Theorem 133 employs only one rule governing all steps of reasoning, namely detachment. It can seem then, on the mechanical reading of Frege's notation, that all the steps of reasoning have exactly the same logical status, that they serve only to make explicit information that is contained already implicitly in the starting points. It's the mathematical reading that reveals the fundamental differences. First, between inferences that merely change the presentation of a formula as governed by a rule of logic, right? That's what we have to do at first. And inferences that combine content from two different formulae by hypothetical syllogism. And also, and more interestingly, between inferences governed by a law of logic and inferences governed by a rule derived from the definition of following in a sequence. Only the mathematical reading can reveal the fact that the proof is, as Frege says it is at once deductive and also ampliative, a real extension of our knowledge. And it does so, I've suggested, because it involves a mathematical construction of the derived theorem. Because the inferentially articulated contents of the concepts contained in the theorem, right? The theorem has only defined signs. Because the inferentially articulated contents of the concepts contained in the theorem are displayed in Frege's specially devised mathematical language, the expressions displaying those contents can be manipulated according to antecedently specified rules to generate the result that's wanted. In that case, just as Frege says, the conclusion is contained in the starting points, not as beams are contained in a house, that is, implicitly, needing only to be made explicit, as you might make the house beams explicit by dismantling the house, but potentially as the plant is contained in the seed. It is the course of reasoning, the act of construction, there's 133 right at the top, that makes the potential actual. If you want more details, those are my books. And there's Frege and Kant. Thank you.
Okay, thank you very much, Professor McNess. So now is the time for questions and answers.
Yeah, that was quite a lot. You might need a moment. We'll put it back to this nice. Yeah. This shows every step in the whole proof. Like there's no gaps in the proof. It's this most boring thing. Everything is spelled out. The little asterisks are where the definitions. You always start with definitions. And then you make changes, right? You make changes to the definitions. And then these heavier lines are joins. They're all by hypothetical syllogism. I just showed you the most interesting parts of the proof. But this is actually all the steps of the proof. And we're just preparing formulae and then combining content, preparing formulae, combining content, until we get the conclusion that we want. That is, I claim, synthetic a priori. So Kant was right. Mathematics involves constructions. But he didn't have the idea that deductive proof could be constructive. That's what Frege saw. So it's a pretty strong claim. Frege's is a mathematical language, not a language of quantificational logic.
So far, Kant and Frege are not so different from each other. Yeah?
Right. I think they understood mathematics.
You have explained that in philosophy we use words, but mathematical language is something totally different.
Yeah.
We cannot use mathematical language in philosophy.
That's right.
But nowadays, philosophers see things differently, I think.
Well, but in
we use the language of logic, which is essentially a mathematical language.
well, but is it?
Studying arguments.
Because really, I think we use so I'm claiming the language of standard logic, the symbols abbreviate words. So wedge abbreviates, or the horseshoe abbreviates if then, and so on. Definitions merely introduce, again, abbreviations. So the claim is, and sometimes Suppies is explicit about this, but I really think that, you could write it all in natural language It's just more perspicuous, it's shorter if you write it in the symbols. But the symbols aren't functioning differently from what people suppose the words of natural language are doing. So people suppose that when I say, you know, all cats are mammals, and when I write universal quantifier CX horseshoe MX, I've just done the same thing. And that's not how mathematical languages work. Kant saw this, and you know, Kant saw Euclid's geometry. Those diagrams are formulating content in a mathematically tractable way. You can reason in the diagram. Well, that for sure is not an abbreviated natural language, right? When you think of that first Euclid 1:1, where you've got the two circles, what it's doing is formulating content. It's the same in algebraic language. 2a plus 2b plus 2c plus ... plus 2n. That displays the content of a mathematical idea, the idea of sum of arbitrarily many even numbers. So what these mathematical languages actually do, they're extremely powerful. They formulate mathematical content in a way that enables rigorous reasoning. The language of quantificational logic does not do that. That's not what it's for, right? It is for a perspicuous representation of truth conditions. But truth conditions are different from the contents of mathematical concepts. So Kant's idea that you can display contents in a mathematical language in a way that enables a construction to give you something new. I'm just saying Frege saw how to extend that idea to deduction. Definitions display the inferentially, it needs to be inferentially articulated now because we're going to do inference. So in Euclid, it's sort of spatially displayed. In elementary algebra, it's the arithmetical content, the calculational content. But now we need the inferential content. We display that in definitions. That requires the Sinn-Bedeutung distinction because you want the same complex sign to display Sinn, to display the content, and to designate the concept. You've got to be able to see it as one whole. No, I'm talking about this concept. But you've also be able to, you have to be able to see it in its parts because you have to break up its parts when you reason. I mean, it's a lot like, if any of you know anything about organic chemistry, a synthesis in organic chemistry, right? You have to combine those chemical bonds. And you have to do it in the right order because if you do one of them too early, it's going to get in the way when you want to do something else. What we're doing is a construction of a formula using the rules of logic and rules provided by definitions in Frege. So I think the fact that we have failed to see Frege was a 19th century mathematician. He's coming at the end of the developments of 19th century mathematics. He's concerned with mathematics. He says this result is synthetic a priori. It's deductive, but it extends our knowledge. We've just ignored all of that and basically said, oh, we already know what Frege's doing. Frege's doing what we already understand. And then we can't understand how it's, and I mean, mathematicians, quantificational language hasn't helped mathematicians. I mean, so yeah, instead of saying for all x, they write an upside down a. But the language has not solved our problems. Frege's language is philosophically interesting in a way that standard quantificational logic is not. So yeah, I mean, Kant was wrong about logic, but he was right about mathematics.
So for Frege's mathematical language, I also have one question. Some people think that Frege's judgment stroke is superfluous superfluous.
Yeah.
Yeah, but some people also don't think so.
And so this is the language itself, or?
No, for Frege's judgment stroke, is superfluous or not?
Sorry, for Frege's what?
Judgment stroke. Judgment stroke. You use that also. Judgment stroke.
Sorry, I'm not getting the word.
Judgment stroke. I use them okay.
Whoops.
This one, judgment stroke.
Oh, okay.
Yeah, judgment.
The judgment stroke, yeah. Okay, no, the judgment stroke is crucial. Thank you. That's a great question. That's a great question. So yeah, Frege calls this is the content stroke, and this is the judgment stroke. And Russell says, nah, we don't need a judgment stroke in logic, right? He says that in the Tractatus. Because in logic, we don't care about what people judge. I mean, judging is just, you know, what I think. That's not what the judgment stroke is. So the content stroke is supposed to give you something that is true or false. So when I I need the content stroke to attach the other strokes to. But when I put this last content stroke here, that is supposed to show that this whole thing has a truth value, either true or false.
So content can also be a question, for instance.
Exactly. But I mean, it's in a way, it's not I mean, it's got to be true or false. So if I put the content stroke and it's neither true nor false, I've made a mistake. Because, you know, if it's false, then I ought to be able to put a negation sign on it and make it true. Now this one is not just me saying, I think this is true. It's me trying to show something objective. Because for Frege, this is, again, he's concerned with mathematics. He's concerned with actually drawing inferences. Well, you can't actually draw inferences unless you start with true claims. So in logic, we only care about the relations between, right, the relation of logical consequence. If the information in the conclusion is contained in the premises, we say the relation of logical consequence holds, and we think that's what logic does. Fine. If you're a mathematician, you want to actually reason. You want to actually prove theorems. And that means you have to start with truths. You're not just starting with claims, you're starting with truths. So when you put this stroke, Frege says, you can't draw inferences if this stroke isn't here. And of course, you can think you've made a true judgment and you failed. So this is always the conditional stroke. This is always the negation stroke. The content stroke and the judgment stroke are different because I can put them on and be wrong. That is to say, I don't have a truth of valuable claim. Or I do have a truth of valuable claim, but it's not true, and I put the judgment stroke, then I've made a mistake. Because I've tried to indicate something as true when it's not true. So for example, Basic Law 5 of Grundgesetze, which is what causes the problem. Frege thought it was contentful. He thought he had something meaningful, and he thought it was true, both of which were wrong. He shouldn't have put the content stroke, but once you put the content stroke, then you think, well, either it or its negation is true. But in that case, it wasn't. So yes, for Frege, as Frege said, Philippe Jourdain asked Frege specifically. He said, look, Wittgenstein says you don't need the judgment stroke. Isn't he right? And Frege said, no, he's not right. You can't make inferences unless you've got judgments. And Frege says, so let's suppose that this, in fact, was not true, right? So I put the judgment stroke, but I'm wrong. Then I can't draw this inference. Frege says, if you don't start with the truth, then you can't draw the inference. It's a pseudo-inference. You think you've drawn an inference, but you haven't.
So the judgment stroke is not superfluous.
It's not superfluous. Yeah, it's necessary.
It's very for Frege.
It's important for Frege, and it's important because what he cares about is mathematical reasoning, not just logic. This is a mathematical language, not just a logic.
Other questions? Yeah.
I am very bad at math, so correct me if I'm wrong. So I think there's a time where you say that for count, if we have 5 plus 7, we get 12. This is a priori, but it's also synthetic. I'm just wondering if this is only a product of how we understand numbers, because we see this as synthetic because 12 isn't containing the 5 and 7, right? But if we understand number in another way, where I think this is also probably Russell's idea, if we understand 5 as the successor of the successor of the successor of the successor of 0, like if we just understand them in a sequence, and then we understand 7 the same way. When we have 12, we just have like 12s and a 0. So there isn't any new concept added to the number 12. And if we just refrain from like counting all the s, then aren't they like analytic? Because they have this like they're applying the same concept in understanding languages, right? Or understanding numbers.
Okay, good. Yeah, it really depends on how you are conceptualizing these things. I think we already see this in, Euclid on even numbers. How should we think about even numbers? How should we think about prime numbers? So I think you're right that it depends on how you're conceptualizing them. For example, we don't think of numbers as just multiplicities, right? Because how are you going to talk about fractions or negative numbers or complex numbers? So that conception of number is a very simple conception. But if your conception of number is as these multiplicities, and if you have this language, right, you show it synthetic a priori because you've got a language that allows you to display the content of the number so conceived. It might well be that on a different conception of number, it's not synthetic a priori anymore. I'm trying to think of an example. We know in mathematics that over time we have to change our conception of what these concepts mean. Limit operations, we change our conception of what they are. And with your changing conception, you change the possibilities for proof. So it's more, it's not going to turn out that everything is analytic. I don't think you could get there. But certainly some things, it's just like some things that seem complicated at one stage in mathematics later can seem trivial because you've reconceptualized the domain that you're working in, and all of a sudden, I think being an even number, the sum of even numbers is even. That practically is given with the rule. So yes, it could turn out in specific cases that if you change your conception, I'm not exactly sure whether that example, Frege would say that he talks about that, essentially that case in Grundlagen. If you just think of each number as the successor, you're still going to have to, as it were, move around the brackets. I think that's what makes it more ampliative, because you've got to form the new concept, right? You've got to form the new number. So you've got successor of the successor of the successor, and then you add one more successor, but you've got to make that part of the number. So yeah, in general that can happen. Whether that happens in that case, I'm not sure. Whether it would happen in every case, that is such a bizarre thought. Certainly mathematicians, right? Mathematicians, once they get to the point where a theorem is so well understood, so completely grounded in definitions that it's trivial, that's when they feel like they're done. So there's certainly advances in articulating the concepts in such a way that the theorem is a trivial result of those definitions. But that in itself is a huge result. So I think, I don't think that affects the fundamental point that mathematics can extend our knowledge by being synthetic a priori, by being constructive in Kant's sense. I think that is how mathematicians work, even when they're reasoning deductively. You know, I mean, a better example would be something like analysis. You know, proving theorems in group theory. You start with definitions. And because of the analysis of concepts, you can combine content from those definitions. It's just that we don't have a language to do that in. We're reporting our reasoning. We're not displaying it. But Frege's language is supposed to allow you to report. I mean, to display.
Okay. Any more questions?
Does Frege also talk about the role of inductive reasoning in mathematics? Because Gödel, for instance, stresses the role of inductive reasoning, because that's the way we find theories. Like Goldbach's conjecture, for instance, we see it in many cases, it applies some, and then it must be kind of general rule behind it.
No, Frege's concern was with logicism. Like Frege, because, I mean, again, if you think of the transition from Kant to Frege through 19th century mathematics, the development, so, you know, 19th century mathematics, all of a sudden, people like Bolzano and the whole rigorization of the calculus, they were discovering that they could give these analyses of concepts that would enable you to deduce theorems logically, as it were, rather than by constructions in the algebraic language, which is what they were doing in the 18th century. So it sort of looked like maybe you could prove everything from logical notions. And that was Frege's project, right? And here, our definitions, nothing in our definitions uses anything other than a logical notion. I still think this is not logic, because giving an analysis of the notion of following in a sequence, that's not logic, that's mathematics. But what we've shown is that mathematical notion contains only logical notions, but how they're put together is of mathematical interest, not, I would say, of logical interest. And in the end, you can't do mathematics without the notion of number, so I think there's mathematical content in mathematics. But at the end of the 19th century, it was a reasonable question whether maybe all mathematical content was reducible to logical content, in this sense, that your definitions would contain no distinctively mathematical notions, just logical notions. And that was Frege's project. And that's why he was so rigorous, right? That's why we have all those gazillions of steps. Every time this is, you know, changing the order of two conditions. We have a rule for that. We do a step of logic to get that. Because he wanted to show, if it could be shown, that there was no extra logical content in mathematics. And that was quite clearly the nature of his project. He wanted to derive all of mathematics from logic. Basic Law 5 shows that you can't. The notion of number is not reducible. You need the notion of number in mathematics. I don't know how much else you need, but you need the notion of number. I don't think you need numbers as objects. I think you need the concept of number, and you need the concept of certain numbers, but I don't think you need actual numbers. So yeah, he wasn't worried about how you actually discover new theorems in mathematics. He was worried about what was the content, the intellectual content of mathematics. And the project was to show that it was strictly logical, and that failed. And I think it shows. I think we now know that no, mathematics is not reducible to logic. As I say, at very least, you need the concept of number, and that's not a logical concept. So yeah, I don't think, yeah, he didn't have the cast of mind that would worry about, as it were, questions of discovery. That wasn't, I think, the way things took him. So he had nothing to say about induction. Not mathematical induction, which he does take care of, but sort of, induction in the sense of coming up with new theorems or new conjectures to prove. I think he would say, look, that's a matter for psychology. That's not a matter for logic. I think that's probably what he would say.
Okay, this is a wonderful lecture. Let's thank Professor Macbeth again.
Well, thank you for coming. Thank you.